Hi, this is a lecture supplement to Straight Line's Executive Black Belt course, Week 6, on design of experiments. We want to talk about what a design experiment is, why you would use such a thing, and just briefly how it works. We'll get more into the details in the actual section that's in your slides. But I wanted to give you a gentle introduction into the what and the why, particularly, before we get going. Now, to understand this best, we've been going through the again with the red. We've been going through the DMAIC method, right? And remember that in the M phase, we're doing baselining, and we're collecting baseline data. And for example, we may be collecting data, over time, maybe 20, 30 points of data, something like that. And at the end of the project, what we'll often do is we'll make our improvements, and then we'll have new data. And what we want to do is we want to compare the new. Maybe we're looking at cycle time. And maybe we'll want to compare the new data that we get with the old. And sometimes that's pretty simple. And sometimes, like here would be a case where it's pretty simple, where there's definitely a step change or a sea change where we made our improvement. Other times it can be potentially not as obvious. We may have subtle changes that are a little bit better, but maybe not all that much better, and so the effect is not easily seen. So we've already kind of taken care of this by using something called a hypothesis test. Remember the dreaded hypothesis test. Generally speaking, we're going to be using like for cycle time, we'd be using maybe a two-sample t-test where the two groups would be the before and the after data. All right. However, if we were looking at a defect rate, it'd be the two-proportion test. However, what might happen if you were contemplating, you've got an improvement to make, and some objections that might happen here is people might say, well, it wasn't really your improvement, it was other things that happened. Like, for example, maybe volume went down in your particular process. If you've got a hospital, maybe volume in the ER went down over that period of time. Somebody might say, well, I think the change was really just due to that. So how would you get beyond that and get past some of those arguments? Well, should be pretty straightforward. One of the ways that you would do that is to use a designed experiment. Now, here's how it works. Before implementing, and this is key, what you might do is you might take a different strategy. That other strategy might be, let's suppose that other strategy might be to have a control group as well as a pilot group during your new data collection, and in that way you could compare the two groups in the same time period. Hopefully that makes some sense. Let's go through a very specific example. Let's suppose that we had a process where we were trying to improve, let's say, a throughput. Okay, and let's say it was something like medical charts completed in a day. Let's suppose you worked for a medical charting company. Per day, per coder. So if this isn't working for you, maybe you can do number of calls in an hour per customer service rep. Or if you're looking at a hospital, maybe you're thinking about throughput, number of patients discharged per hour, or number of beds freed up per hour, something like that. And let's suppose you were looking at a single factor that you were going to make an increase of, a job aid, adding a job aid to it. Okay, so you had a job aid that you were going to put into the process. You're going to let in this case, the coders use it. and it was going to improve the throughput. You could do this in two different ways. Let's suppose the most obvious way is just to have everybody do it and look at the before and after picture. And that's the typical way that people do it in a Six Sigma process. However, another way that you could do it is you could have you could put a medical chart, which I'm going to draw right there. There's my medical chart. And it's going into and just imagine here for a moment, it's going into something called a randomizer. And you'll see what my randomizer is in just a moment. And the randomizer is going to spit out either you've got a pool of coders here, and either this coder is going to code without the job aid. Maybe there's a 50% chance of that. And there's a 50% chance of coding with the job aid. Hopefully you're with me on that one. And then in each case, they would do it for a single day. And in each case, we would then measure. Maybe it's not the chart, but it's the day. And each day they would either this particular person would either randomly do it without the job aid or with the job aid. Okay, or I would randomly select one of these guys. Okay, and I would get the throughput with, if I had something, if I collected, let's say 16 days of data, I would get the throughput with, and I would get the throughput without. I guess a better way of simply doing this would be to break into two groups and randomize each of the people that we've got into one of the two groups. That would be a better way to perhaps randomize it. If you were doing it in process, you'd want to do it on a chart. But you select a person and randomly they're assigned to one of the two groups that are going to use without and with. Let that run for a certain amount of days, and we'll look at the throughput and we'll compare that. Essentially, what we've done is we've run a one factor. What we're going to learn is that this is a factor. The job aid is a factor, a single factor design of experiment or design. And you see that we've randomized it. Now, those of you who are used to looking at clinical trials data or things like that will see right away this is nothing other than a unblinded. In this case, we know what we're doing here. An unblinded randomized experiment. Double-blinded is usually if you're doing drug trials and things like that. The experimenter and the recipient of the treatment doesn't know what treatment they got. In this case, certainly a coder would know whether they're using the job aid or not. So that would be difficult to do in a blinded situation. But that's okay. We've still randomized it, and that makes a difference. Okay, and the point of this is that we can compare then the two groups in the same time, right? During the same time period, we can compare throughput with and throughput without, so that we can do a fair comparison, right? If we did our means chart, and let's suppose remember our means chart looked blue, I think. So I'll make it blue. It's in Excel stats. So if our means chart looked like this, the throughput with was this one. This is with, and the throughput without was here. And we had our, our handy dandy, confidence intervals here. It looks like we'd have a winner, and so we'd keep the change. And we could be pretty sure that it was the job aid that caused the difference between throughput, which is different than what we've seen before. So that's number one. That's actually a very simple design experiment, and so you can see sort of why you'd want to do that. That's called a one-factor experiment, and generically, what we're going to do is a one-factor experiment has the following characteristics. It has a response. We usually call this our Y variable, right? In mine, it was throughput, in my example. And then we have factors on this side. In this case, it was, usually we label them A and B and C if we have more than one factor. Okay, we'll come to the point where what happens when we have more than one factor. Okay, but in any event, in ours we had the job aid, right? That was our first factor. And how do we run that? Well, we ran it at 2 levels. So job aid had 2 levels. It had a low and it had a high. Now nominally, this was without or no, and this was with. This was without. Let's go back and try this again. This was without, and this was with. Okay? Now the beauty of this, so right away what we've discovered is by doing this sort of pilot, where we've held off and then run it with a pilot group and without a pilot group, that what we've been able to do is we've been able to establish cause and effect. And that can be pretty important sometimes. We proved that it was the job aid that did it. Of course, if we still need to collect some data to show that. But here's the real kicker. What would happen if we had other factors, like, for example, batch? Perhaps we were giving the coders a batch of, here's 30 or here's 40 charts for you to work through for the day, and go to it. Maybe another improvement was the batch size. Maybe instead of doing that, we give them 10 at a time. And after they finish the first 10, then they can get the next 10. And after they finish the next 10, then they can get the third 10. The idea is seeing that there's a certain incentive that they can see a little bit better 4 times a day instead of once. Another idea would be to have them use 2 screens. I'm just going to put number of screens. So how would we test this? Well, this seems to be more complex, because what we'd need to do is we'd need to be able to run each of these while holding the other constant, and it would seem to us that this would take a long time, because we'd have to have a control group and a pilot, and we might have to do 3 times. So what do most people do in DMAIC? What most people do in DMAIC is they implement all of these solutions at once. What happens then? The problem is, suppose that the process does get better, the throughput does go up a little bit. Was it the job aid? Was it the batch size? Was it the number of screens? Which one did it, and to what extent? And what if we had some solutions that actually didn't work and made it worse? We wouldn't be able to tell that. Maybe we could even improve the process even more by not doing those, but by doing some of these in combination. So how would we do that? Well, that's where design of experiments really comes in, and it allows us to test all of them at the same time if we do it in a orderly fashion, and if we and it also allows us to understand how the factors interact with each other and by how much. So it does all of those things. So it's really very powerful. So how does it work? Here's how it works. We start out by mapping all of our factors, our A, B, C, our batch size, our number of screens, in the following way. So batch size might be small and large. Okay, number of screens might be 1 versus 2. Okay, and we map these. These get all mapped always to A, B, and C. Okay, now if you're doing your example in the ER and you've got 3 factors, you've just now converted it to this abstract thing that says A, B, and C, and so it should be the same thing that we're looking at right here. We also convert these to a low and a high of the following, and this is why I use the notation low and high. -1 is always low, +1 is always high. So -1 + 1, -1 + 1. Okay? So that's the beauty of this, is that regardless of what we have right here, we end up with a generic one of A, B, and C, where our low and our high are -1 + 1, -1 + 1, -1 + 1. All right. Now, how would we run our experiment? If we have this, keep in mind that this could be your process, or we could still have that coding one. How would we run this experiment? Well, the most obvious way is to simply say, what if we ran each and every one of the combinations together? So in other words, let's take all the A combinations, all the A combinations with B and C. We would have A of -1, a B of -1, a C of -1. We would have an A of +1 with a B of -1 and a C of -1. We would have an A with a -1, B of +1, C of -1, an A of +1, the B of +1, C of -1. And you can see what I'm doing here, right? So this then becomes a -1, +1, -1, +1. This becomes minus, plus, plus. And this becomes plus, 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 plus. And in this case, all the combinations are covered. So again, if we had a group of people set at minus, 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 a group of people set at plus, minus, minus, and so on, we would have all, in this case, 8 conditions, right? This is we'll call this trial or run. We'd have all of the 8 trials, and we'd be able to separate out all of the different things. Let's see how that works in practice using a tool called DOE Helper. Okay, so we're going to go ahead and do that. And I've got to open up my example and DOE Helper. I'll open up DOE Helper first. You have this. And this is a piece of code that I wrote a long time ago, so please be kind. It's very rough. It's meant to just use in class. And I'll show you how that works. And let's go to our example for a process. And let's suppose that this, I'm going to hide this column for just a moment. Let's suppose that this was how we did it. So in this case, what I've got is, the first thing I've got is I've got my runs. Very often, if you're doing things in order, you'll want to randomize that. But in this case, we would randomize who is selected as -1, who's going without the job aid versus with the job aid, who's using a large versus small batch, who's using the 1 screen versus the 2 screen. Okay? And let's suppose that we let that go for 16 days, and we measured the average throughput of each of our groups. Okay? So let's suppose that the average throughput of each of our groups was, again, without a job aid, and with the with the small batch, and with 1 screen, our average response was 27. Again, this would be A -1, B -1, C -1 was 27, and so forth. The people that were using the job aid and who were using the small batch, should put in here small versus large, just to get the order right. There we go. Okay, small versus large batch. They were using the small batch, and they're using 1 screen, and this is the difference. Okay, so how would we take a look at that? Before we go on and use DOE Helper, because DOE Helper will do this for us, I just wanted to see how would we be able to separate out the effect of A and the effect of B and the effect of C. The short answer is we would average at the, it's actually not that bad. We would average at the lower level and then subtract off the average of the higher level. Or we could just average over all levels. So for example, and we would want to see how much different that is from the mean. So let's start out with the mean effect. The mean effect is simply the average of all of these. And there we go, 34. So the mean effect is 34. Let me put another decimal point on that. There we have 33.8. Okay, it's close to 34. How about A? Well, the effect of A would simply be all the pluses minus all the minuses. The average of the pluses minus all the average of all the minuses. So it's the average of the pluses. So the pluses are 38. Oh, there's another 38. There's a 36 and a 37. Okay. All right, so the average at the plus side is 38. Or, I'm sorry, 37. I'm going to try and format these guys. 37.1. Now, how did I do that? What I did was I took all the pluses of A. Those right there, the ones in yellow that I've just made yellow. This is the average of all the A's. And now I'm going to average all the minus A's. Okay? Now I'm going to average all the minus ones. I'm going to subtract those two averages, minus the average of all the minuses. So it's this one, this one, this one, and this one. And that tells me the effect of A. In this case, the effect of A is from going from minus, that is no job aid, to using a job aid is a throughput of 6.6. So using a job aid actually improves my throughput, my daily throughput, 6.6 charts. Okay? That's what it is. And hopefully that makes some sense. I mean, we set up the minus signs and we set up the plus signs. Right? Now let's take a look at B. This would be equal to the average, whoops, type it in correctly, average of, we're going to do the pluses minus the minuses, right? This, minus the average of, oh, come on, of this. The effect of B is a little bit smaller. The effect of doing the small batch versus the large batch is actually a little bit smaller. It's actually 3.6. And finally, how about the effect of C? This is equal to the average of all the pluses minus the average, spell it right, of all the minuses. Much smaller. In fact, it says it's a negative effect. All right, so now how would you say which one had the most effect? I'll put the plus ones in yellow here just to emphasize what we did. There we go. So these are some of the average effect, the effect of A, and the effect of B, and the effect of C. Now, which ones are the most important? Well, the short answer is the ones that are the biggest. So obviously there's some average effect, and this is kind of like, well, what was the average over those weeks of all of them? So if you have to improve above the average, right? The effect of A was pretty big. The effect of B was a little bit smaller, and the effect of C was pretty small indeed. Now, maybe, in fact, C didn't do anything, and this turns out to be statistically insignificant. More on that to say in just a moment. Okay. On the other hand, though, we can also look at a few other things, and we can also look at the interactions. For example, is using a job aid versus not using a job aid, is that dependent on whether you have a small or large batch or whether you have one or two screens? Sometimes that can be synergistic. Sometimes that can be anti-synergistic, okay, or negative. So let's take a look at that. How would we do that? Well, it's actually pretty straightforward, and so I'm going to show it to you. Whoops. I'll show you one, and then we'll use DOE Helper and let it kind of take us away. There we go. So I added a bunch. Delete. Okay. We would pretend that there is such a thing as an AB thing, and it's essentially equal to A times B. Okay. So again, so -1 times -1 would be +1. And if I copy that down, 1 times -1 is -1. -1 times 1 is -1. 1 times 1 is +1. And you can see the point. We could calculate the AB effect, and that would be equal to, again, the average of, and not in this time A or B, but the average of AB. Oops. The average of all the ones the ones in the AB column. Yeah, I better do this again just to make sure I got it all. There we go. Minus the average of all the -1s in that column. And there we go. So the AB effect, now look at that. The AB effect is actually pretty big relative to C. It's more important than the two screens we're finding. So the interaction of the job aid and no job aid really does depend on the large batch. It looks like if you're using large batch, this job aid is not so helpful for you. Okay, we could continue down the whole thing and do the AC and all that, and again, this would just be simply A times C, and we play that same game, and we can calculate the AC effect, which is equal to the average of all the ones minus the average of all the -1s. Okay, and we can see that AC is small. Okay, so again, in theory, we've got only two more. Whoops. We've got only two more. We've got the BC interaction, and we've got the ABC interaction. Okay, I'm not going to do those, but instead, I'm going to show you how to do them in. I'm going to show you how to do them in DOE Helper. In DOE Helper, essentially, what you do is you take all of your factors, A, B, and C. Not AB. You don't actually have an AB factor. You just have A, B, and C. Okay, just these three: job aid versus no, small batch versus large, and one screen versus two screens. Okay, so let me hide those. Those are dummy columns that are necessary for that. So what we're going to do is we're going to copy this. Well, first of all, we're going to open up our DOE Helper, and we have to go to the number of trials that we ran. In this case, we ran 8. This looks kind of nasty, but you'll see that what we're going to do is we're going to copy and we're going to paste, and we have to keep what's called the standard order. Don't worry about that. That's exactly the -1s and pluses that we put in. And we're going to plop in our ABC right here. We actually don't have to do that. We could just put in the response. But I'm doing this just to show that that's exactly what we're doing. Okay, now we've got our experiments that we ran. And let's go into a process example. Now I've got to copy the response. Put that in there. you'll notice that you get these. Click the Run the 8-trial analysis. In this case, it gave us the same answer. You see it also popped in a model there, and it says the following. Let me zoom in a little bit. It did the analysis. And what it does is it shows you all of the factors here that are in the model. Now you'll notice that it has something called D. We didn't have a D factor, did we? We only had A, B, C. It has E, it has F, and it has G. Let's just hold off on what those are for just a moment, and then we'll come back to it, okay? The things that are marked red are, it's an estimate that they are statistically significant, okay? And at the top, this tells you the value of the model that we have. Now, you should recognize some of these numbers here. You should recognize the 33.8. Maybe you might not recognize this 3.31 because it's half of what we had in our spreadsheet. There's a reason for that, because the model is a movement away from the mean, not simply the mean. I'll draw a picture of that in just a moment. And in any case, there's our A effect, 6.62. We go to the DOE process example. There, let me put another decimal point on that. Okay. And I'll paint that, so let's format that. There we go. There's my 6.62. It says the B effect is 3.64. Let's see if we got that. 3.64. There it is. Okay. So it's all the same, and there's my D. So, and it turns out that C is not statistically significant, so it doesn't appear in our model. So the interesting thing is, if we're going to try and optimize this, which is what we should do, we're not going to consider C at all in our optimization. So it actually turned out that C, despite the fact that the overall throughput might have gone up, C turns out to be non-important. All right. And now, what about this D thing? What is that? Well, since these didn't appear in the model, D through G, we'll talk about this in the full lecture. But since D through G didn't appear in the model, what we can assume is that these are terms for the interaction. Now, the only ones that we really care about are the two-factor interactions. So let's see what they most likely are. Okay, a two-factor interaction is going to be what it is only if both of these other terms appear in the model. So let's take a look at D. D was the one that was significant. It could either be the AB interaction. So in other words, these did not appear. I'll color those yellow. It could either be the AB interaction, the CG interaction, or the EF. Well, since G doesn't appear and such E or F don't appear, it has to be the AB interaction. Likewise, if we found that E was significant, it could be the AC, the BG, or the DF. For those of you still with me, you should realize that it has to be the AC interaction. Okay? If you went through the whole thing, you'd find that F was the BC, and then the only thing that's left over, if you really were interested in the three-factor interaction, is G. G turns out to be the three-factor interaction. Okay, so that's it. We could then copy this. There's some residuals analysis too. Do you see any patterns? I don't see any patterns. We could then copy this and paste it into our process example. I'm going to paste as a picture, all right? And then what we can do is we could type in our model, and we could try and optimize with this model. But there you have it. There is the soup to nuts, how you would analyze a DOE. We did it by hand and so forth. Now, I do want to say what's happening with the interaction. Well, with the interaction, in order to optimize, now an interesting thing is, when you have an interaction, you're always thinking about, I can never optimize this process without thinking about that interaction. So that just says small batch versus large batch, and it essentially says that if I have a large batch, my job aid is not as effective. So good thing my process is actually improved. If we look at it, we would say I want a plus here, right? I want to use the job aid because that would tend to increase. I want to use, this would say large batch, but this would say, if I'm using the large batch and the job aid, it's almost a wash. So I might want to come back and really look at my process. Is maybe the large batch is not the thing that I want to use, or maybe I have to create another job aid specifically for the large batch, or whatever. Okay? But basically that helps you isolate all of the effects and the interactions with them. All right, now one last thing before we stop here, and that is I wanted to draw to you what's really going on here. We can look at, for example, the model, which was something like 34 plus, oh no, I've got to go back, plus 3.3a, 1.8b minus 1/6. Okay, got it. Plus 3.3a plus 1.8b and minus 1.6 AB. Remember, and then A, of course, we had the job aid and we had the batch size, and we had this third thing, which was the screens. So in other words, if we're going to have to spend money for the screens, we'd rather not do it. It's not effective. We can tell that, and that's our throughput. Okay, that's our Y. All right, now what it does, you'll notice, is that this is a -1 to +1 model. So if we're looking at the relative effects of this, the relative effect is it swings 6.6 between the minus and the plus. So if we look at the effect of A on the minus side and on the plus one, the difference between that in terms of throughput, like we're drawing a picture of throughput, A would look like that. There's a big swing. There would be my 34. This would be 37.3, and this would be, I guess, 31.7. Okay, so the total swing is 6.6. All right, so hopefully we covered the what, why, and how sufficiently. DOE, keep in mind, is a great way to run a pilot, even if you have one factor, thinking about randomizing who's going to be in which group and then testing them at the same time. Very, very helpful. Very, very helpful. And we talked about that the why you would do it is also if you have more than one factor that's in there, this is a great way to get many different control groups in there and have your results statistically sound. We also talked a little bit about how, but more on that in the next lecture and in the slides. Okay, take care, and we'll see you down the road.